Well, hey everybody. I don't have my camera on right now because I'm using my other camera, my document camera, to show you this. I thought it was a good idea since it was a few weeks ago that some of you were starting chapter 29 to kind of just run through the first couple quizzes. Most of you have done those already, and I realize like I have some of them. So let me just run through and remind you what you needed to do on those because we don't want you to forget all that stuff. So here's a couple of the quizzes like what you took. So the first part was figuring out the direction of a magnetic field that would be created by a moving charge. And this moving charge could be in the form of, like, on this quiz, it was a single point charge, or it could be like a line of current, which is just another name for moving charge. So I'll give you a dot somewhere, and then you do a cross product with um, the velocity vector and then what we call the r vector, and that tells you which direction the field will be. So it's going to always be perpendicular to both of those. So in this kind of problem, it's perpendicular to the page. It's either in or out. Here's one that's out, and here's another version that ended up in. Okay, I've covered up the names on these, but they are actual student ones. And then there was the numerical part of using the Biot-Savart law. This is one that is very calculus-y, but in a couple of instances, the calculus really simplifies quite a bit. So like on this first version of the quiz, this was something that a lot of you didn't do right the first time, but it's not hard to do because the calculus ends up being pretty trivial. So if I give you a loop of wire like this, just a circular loop, imagine taking a wire and just kind of turning it into a circle and connecting the two ends, and somehow we're going to magically get current to flow. Like in reality, we'd have to have like a battery in here or something like that. But it just makes a letter O, and it's only trivial if I ask you for the magnetic field at the very center. So the field is either in or out, and then when you do the calculus, the reason it ends up trivial is because there are no real variables here. Like R is not actually a variable, and neither is I, and so everything simplifies very nicely. So this would actually be not dB, but B. The difference is dB is the field created by just a little tiny segment of the loop, but then when you sum together all of the little effects of the loop, all the little fieldlets we might call them, that's what the integral would look like, then it ends up being the actual total field from all the little fieldlets. Okay. The other way we would use the Biot-Savart law, and this is one I wouldn't expect you to be able to do from scratch, but to be able to kind of reason through a long line of current like this, if I give you a spot and say, okay, tell me about how strong the field is at that spot there, you would have to do several things, and that's what this part here is. You can like freeze that and look at it if you want to. I'm not going to go through the whole thing. Similar kinds of questions. Here's something I put on the second version of the quiz, just to be able to draw what a magnetic field looks like. So circles, when you look at it from this perspective, sometimes we have to use dots and X's instead. Or if we look directly at the wire, then it's a lot easier to draw those. The circles actually look like true circles. And then if we have a loop, here again that's that same kind of situation that we had here, the field at the very center, but this time it's not at the very center, but somewhere along the axis that goes through the center. So there's still a little bit of calculus to do there, and that's what this here is. This is a well done example, which is why I picked that one. So again, you can kind of look at that. This has some markings on it from when I went over it with the student, but so that's most of first part. The second part was about dipoles, and so one thing I like to emphasize is the comparison between an electric dipole and a magnetic dipole. These are a lot easier to draw. This gets kind of tough because it's in 3D, but we've got like a loop here, and then you have to figure out from my description, when we look at it from below, you got to be able to tell like what everything is. So here on this quiz, we had a north pole facing down, so I would actually put my thumb down and then I curl my fingers, and then depending on the perspective I take, like when I look from below, like, oh, you can't see this very well, but when I look from below, like where my thumb is, it looks like my fingers are rotated counterclockwise, and when I look from above, like up here, then it looks like my fingers are pointed clockwise. So it's very much a perspective, and that's why you have to know where you're looking from in order to be able to draw the current. So for north to go down here, to be looking from below, you would I'm going to see if I can do this. Oh, I'm going to be upside down. That's not going to work. I was going to kind of show you what I was doing in the air, but Yeah, that won't work. You have to kind of like get under your hand and have your thumb pointed down towards your eyes, and then it would look like it was counterclockwise, which is what I drew like here. Again, it's kind of hard to see. Dipoles are calculated using a pretty simple equation here. I'm going to write it bigger just so you can see it. So it's a vector. Unfortunately, we use mu again. We've used mu for so many things in here, but this one is a vector, and it usually is bolded when you see it in text. And it's got a little b next to it to remind you it's a magnetic field, or dipole, magnetic dipole. So it's the current flowing through a loop in the area of the loop. And it turns out any shape at all will work. And why did this freeze? Oh boy. Well, I've been fighting with my document camera here for a little while, and I finally gave up and decided I want to finish this. So it's actually a few hours after I started it. I'm going to kind of go a little old school here and hold up this quiz. So this was the last part of the quiz, number 2. Again, most of you have finished this, but that's going to be really hard to read, isn't it? Basically, it asks about how the magnetic field of a magnetic dipole is affected by distance. So I'm talking about a loop here. Again, like picture that loop of current, and where are we? The farther away you get from the center of that loop, the weaker the field is. Well, how much weaker? Turns out for a dipole, kind of like an electric dipole, it's an inverse cube relationship. So, you know, lines have inverses, and like point charges have inverse squares. Well, dipoles have inverse cubes. So the question on the quiz was something like, what happens if you move, 4 times farther from the center of a dipole than you were before? How much weaker will the field be? And the trick is you cube that proportion. So 4 to 1 cubed is 64 times weaker when you're 4 times farther. So that's the nature of that. So that was about all I wanted to go over, and so hopefully that's enough. If you want to, review some of that stuff, let me know. I can return a quiz to you. I have the quizzes that you turned in on that last day before we left. Or maybe you just like want to redo a quiz if you don't have it with you, or whatever. If you just want to feel like you know that stuff. I'm not going to change your grade or anything. You can keep your grade. Just take it for your own benefit. So all right, I'm going to let that go here, and hopefully we get this posted soon for those of you who'd like to see it. So thanks for watching. See you soon.